Welcome, very good morning. We will discuss today factor scores and case study under factor analysis. We will see the species based case study, and we detail the what is factor scores and what is confirmatory factor analysis. Let's go to the next slide. I hope you are enjoying the lectures.
That means factor loading will not reduce the explanation power. It will keep the same amount of information from the variance explanation point of view, but from interpretability point of view it improves. Then what are the different types of transformation possible? One is orthogonal, another one is oblique. Under orthogonal, the most commonly used is Varimax rotation. There are other methods like Equimax, Quartimax, but Varimax is more popular, and Varimax basically tries to, suppose if my row wise I am putting the x variables and column wise I am keeping f1, f2 like even the factors, then the purpose of Varimax is that it will try that x1 must be loaded with one of the factors. That means suppose if x1 is loaded with this factor, let it be this, but all other cases it is 0. Similarly, if x2 loaded with f1, fine, all other cases will be 0, but the some other can be loaded here, all things will be 0. So, like this. So, that means it will allow some of the factor variables to be highly loaded with some of one factor, and then rest with other factor, rest with other factor, like this a clear structure is visible. So, that is the advantage, and that is what we want also. For Varimax rotation, there are some formulas available, and these formulas you can go through any standard book. It is possible, you will be finding out those things. Okay. Once you have completed all those things, that means all those things means what I mean to say, you know your factor model, you know your number of factors, you are satisfied with that number, you have seen that the adequacy of the model is properly tested and they are adequate, your even but large sample test is also satisfactory, all those things. So, factor models now can be used for some other purposes also. What is the other purpose? Other purpose is, suppose if I go for orthogonal factor model, so whatever factor you are basically obtaining, they are independent each other. So, like principal component analysis, these factors like principal components can be treated in a subsequent regression analysis where this will be used as independent variables. In that case, what is required? You require to know what will be the values of all those variables. So, if you want to know the values of the factors obtained, these are known for every observations related to x, these are known as factor scores. So, pictorially what we can do, we can write like this, that you have collected n number of data points and you have x1, x2 to xp number of variable or manifest variables. For every one you have collected the data and you have created factors with this data set FM. You are interested to know that for my ith observation, what are the values of F1, F2 and Fm. For example, if I say this is I1, Fi1, Fi2, like this Fim, this is a I can say multivariate observation, ith multivariate observation on all the factors. But these observations are not direct, because you are observing directly this x and you are using factor model. This, then there is a engine, this is basically created through the factor model, factor model. This is observed, actually these are unobserved, but you are finding out these values using this. These are known as, so for the first one then it will be F11, F12, F1m. For the second observation F21, F22, F2m, or like this. For the last observation Fn1, Fn2, Fnm. So as a result, you are having a data set cross n cross m, which are known as factor scores. Factor scores. Fine. Now, how do you get this factor score? What are the methods available? If you see the factor model, x minus f equal to x minus mu equal to lambda f plus delta. What are the things unknown? Your unknown thing is this is also unknown, this is also unknown, this is also unknown. Only you know this side, again this one may be x bar. So, though it looks like a regression equation, but in regression equation you know y equal to beta x beta plus epsilon. So, there you are interested to find this one, this x was given, y was given, but it is not like this here. So, this structure is complicated. Now, finding out this factor scores, what I can say that Fi cap, it is a difficult one, but there are certain methods like weighted least square method is there. You can go by the, as it is regression like equation, so regression methods you can use, and maximum likelihood methods are there also. So, several methods are there, and if you go through good books like Johnson and Wichen book, Applied Multivariate Statistical Analysis, these three discussions are given, that how to go for these factor scores. Okay. Then our, as I said that what we have computed, that means the adequacy part is over, factor rotation and factor scores and use of factor scores is like this. Then what I want to just add little more about the confirmatory factor analysis here. In explanatory factor analysis, you have m factors and there are p observed variables, and you are linking each like this, and when it is orthogonal, there is nothing like nothing, but when it is oblique, there will be relationship between the factors. So, orthogonal and oblique. In confirmatory factor analysis will be similar, but with a very important difference. This difference is I know what are the factors linked with which variable. Getting me? So essentially, if I take only two factors with three variables, suppose that three factors with suppose x1, x2, x3, x4, x5, x6, x7, x8, x9. Okay. Then this is my lambda 1 1, lambda 2 1, this is my lambda 3 1, then this one is lambda 4 2, lambda 5 2, lambda 6 2, this will be lambda 7 3, then lambda 8 3, lambda 9 3. This is delta 1, delta 2, delta 3, delta 4, delta 5, delta 6, delta 7, delta 8, delta 9. Correct. Now if I want to write down the equation, you can write down like this: x1 minus mu 1 equal to, what will be, lambda 1 1 f1 plus delta 1. x2 minus mu 2, this will be lambda 2 1 f1 plus delta 2. x3 minus mu 3, lambda 3 1 f1 plus delta 3. Now x4 minus mu 4 will be lambda 4 2 f2 plus delta 4. Okay, so let me do little manipulation here. This equal to, this is related to f1. Now f2, let it be related to f3. So what is happening here then? This x4 minus mu 4 is lambda 4 2 f2 plus delta 4. Similarly, x5 minus mu 5 will be lambda 5 2 f2 plus delta 5. x6 minus mu 6, x6 minus mu 6 equal to lambda 6 2 f2 plus delta 6. Then your x7 minus mu 7, x8 minus mu 8 and x9 minus mu 9, if you write, these all will come on here. That x7 minus mu 7 is lambda 7 3 f3 plus delta 7, then lambda 8 3 f3 plus delta 8, lambda 9 3 f3 plus delta 9. So this is, we are talking about under confirmatory factor analysis. So as a result, if I see this in terms of matrix, what you will get? You will get x1 minus mu 1, x2 minus mu 2, 2, x9 minus mu 9 this side. This side, that structure is very interesting. So for, see, x1 minus mu 1 for f1 you are getting. So that means this is lambda f1, f2, f3 will be there. So this one is your 9 cross 1, this will be 9 cross 3 and 3 cross 1 plus your delta will be delta 1, delta 2, so delta 9. And this is the case. So what I want, x1 minus mu 1 equal to lambda 1 delta 1. So lambda 1 f1 is there, f1 is there here, 1 1. What will happen? 0. Then lambda 2 1 0 0. So similarly 0, I think how many things are there? 3 probably, 3, lambda 3 1 0 0. So similarly finally last one also 0 0 lambda whatever is 9 3. you will be getting first 3 here 3 variable, then 0, second 3 variable you will be getting here 0, third 3 this will be 0, here you will get some values. So you are not getting all the lambda values because which is not required, that is the difference. That is the difference. And another important difference will be here that we want, particularly for confirmatory factor analysis, we want this also, the covariant structure will be there. So that means this will be my phi 2 1, this is phi 3 2, this is phi 3 1. Phi 2 1, phi 3 1. This structure also we want to keep this. Okay. Now then if I go by the factor analysis that x minus mu equal to lambda a plus delta, then what will happen? We found out finally that sigma is the covariance of x, which is ultimately expected value of x minus mu transpose. And then we ultimately what we have found out? We found out with for orthogonal case lambda transpose plus psi we found out, because in between there was an I. When we have created there is an I. So that I is nothing but expected value of F transpose. Okay. Now in confirmatory factor analysis, not only we are doing this type of that so many coefficients lambda loadings are 0, apart from that there is variability amongst the F. So this will not become I, this is not I, rather this will be your phi. So then what will happen? The covariant structure will be this phi, this plus psi. So confirmatory case, why it is? Because we are going for oblique factor. Okay. So keep in mind that there is definite purpose here why we are going for oblique, because it is basically we want to measure these factors as well as their interrelationship. This interrelationship is of importance, is very important for all of us. Otherwise there is no difference. Suppose if I go for exploratory factor analysis orthogonal, then this plus psi, and confirmatory factor analysis which are talking oblique, this phi, this plus psi. Phi is the correlation matrix for the factors. Okay. Now with this I say that we can now prepare to see software. Let us see SPSS. Last class I have shown you SPSS, this class also. Let us see SPSS, that how SPSS can be used for factor analysis. Any question? If you have any queries, so we can discuss, but please keep in mind few things for factor analysis. What is factor? Factor is unobservable or hidden. We say these are the causes, can be estimated through manifest variable x. There are estimation methods principal component method, principal factor method, maximum likelihood method. The covariance structure is this, where this is loading matrix, this is the specific variance, this is your original variance. You may go for S, and that also then you will estimate using one of the method. There are several tests. So, factor adequacy, keep in mind your factor rotation, factor scores, then types of model, exploratory, confirmatory. Okay. Now, let us see this one. I will take one data set straight away from here, and let this data set is like this. Okay. So, there are, suppose there are 1, 2, that 7 variables. I want to do factor analysis. So, in using SPSS, go to analyze, then I think under dimension reduction. So, go to analyze, then go to dimension reduction, then click factor. Then here it will be asking that what are the variables you want to consider. We want to consider D to CH, all variables. Okay. And then there are many other things like descriptive, that variable you may be interested, variable description, initial solution. You may be interested to know coefficient, standard, determinant, KMO and Bartlett test. KMO test is there, which is known as that Kaiser-Meyer, O stands for Olkin probably, that Oaklin, Kaiser-Meyer Oaklin test. So, that is fine. Then extraction, which method you want to use. We have discussed principal component, maximum likelihood, principal axis factoring. These three we have discussed. There are unweighted, general least square, many things are there. Let it be principal component. Then scree plot, you may be interested in covariance matrix. Now, what will be your extraction criteria based on eigenvalue greater than 1 or fixed number of factors. Okay. So, let it be eigenvalue greater than 1. So, what will happen? Let us see. Then rotation you want to know, yes, let there will be varimax rotation. Then you go for scores, you want score, yes, you save as variable. If you want to know the vector score coefficient matrix, click here, and then there are several options how to deal the missing values, what is the display, that is possible. Okay. So, click OK. Now, descriptive statistics, mean standard deviation, then correlation matrix is given here. Now, see the correlation matrix first. There are many correlation coefficients which are greater than 0.3. Okay. Now, that Kaiser-Meyer Oaklin sample adequacy test, based on that approximate chi-square, that degree, Bartlett test of ferricity, significance is 0. It simply says that this data set is factorable, and sampling adequacy test value is not rejecting null hypothesis. Yes, the data means it can be captured. Then the communalities, I think at this point in time you are very much able to explain what is communalities. So, extraction, then initial, raw and rescaled. Rescaled means with respect to standardized variables. Now, total variance explained. If you see here, ultimately these are you can go up to maximum 7 components, but first component's percentage variability explained is 47%, second component explaining 22%, the two in total they are able to explain 70% of total variability. And as we have seen, we have basically selected that we want the eigenvalue criteria of 1 or more using correlation matrix. So, that is why the these two factors we are keeping here, and please remember we are using here basically the covariance matrix in the raw data, rescaled data, that is what is the correlation matrix. See here the values are like this, but here this values is 2.31 and 1.24. So, two factor model is possible because 70% of variability of job stress component, if I can explain using two factors instead of three factors, it is not bad, we can go for that. Now, scree plot will tell you that where do you want to, I think that three factors will be better because LO is coming here. So, that means this is not 1, but it may be more than 0.7, because that Joliffe book I have found that he says that if we go for eigenvalue of 1 or more criteria, then what will happen ultimately, you will find out that many factors to be excluded. So, he suggested that go for 0.7. 0.7 is better. So, go for 0.7. So, that means three factors can be extracted here, and that will give you little better structure. Now, these are that component matrix, your raw component versus scale component, that loading factors is giving here, and your rotated component also given. First one is this one is your original case, this is your rotated case, and component transformation matrix using rotated factor. So, under rotated case KMU, Bartlett test, all those things are giving, again it is repeated. And what is more important here, I think we have not taken this one, that the plot, this factor, that component plot we have not considered here, okay, but you can probably do. So, now I am going for three factors because we found out that three factors may be a better one. So, let us go to this extraction, I will write fixed number of factors, that is 3. Then okay, principal component let it be, then rotation let it be, loading plots, now I am giving loading plots, okay, rest I am keeping as it is. So, come to this, so what is happening here, your 81% of variability can be explained if you go for three factors, it is a better one. And now after that I will show you that component loading plot, okay, 3 component at a time plots are giving, but it will be better if we go for 2 component at a time, that will be much better, visibility will be much better. Okay. So, I think in SPSS it is very easy to conduct factor analysis, provided you know the theory behind it, otherwise what you will get, you will not be able to interpret properly. Confirmatory factor analysis, there are for confirmatory factor analysis there are many other methods of estimating the model fit. What I can say, that model adequacy, what is the model adequacy, that you want to estimate, that is possible through different methods, different index are developed, but there those things I will be discussed in structural equation modeling again, and which are equally applicable to confirmatory factor analysis. Thank you very much.